Okay, so this is going to be the video for 8.1. So chapter 8 is called Polar Coordinates. And parametric equations. Now, up until this point, we've kind of just been doing trigonometry for the sake of trigonometry. Just, you know, we've learned how to deal with trig equations and their inverses and their graphs and their equations and their identities. But mostly it's just been, we haven't really gone outside of trig, right? In fact, we haven't even really done that many real-world problems, but that's okay. This chapter is, I wouldn't call it an application chapter, though it could certainly be applied, and it certainly is in the real world applied. But we are not just doing trig for the sake of trig anymore. We're using trig in other areas of mathematics. So in particular, in chapter 8, we're going to be looking at polar coordinates of numbers. So in other words, describing a number not just by its xy position in the coordinate plane, which is how you would normally say the position of a number in 2 dimensions. You would give its x and its y coordinate. We're going to be talking instead about a different way of writing the position of a number in 2 dimensions. And then in 8.3, so we are skipping 8.2, 8.3 is called polar form of complex numbers. So that's, again, where we're looking at, we'll use, our tool set will be trig, but the goal will be to look at complex numbers, which by their very nature have to be graphed in 2 dimensions, and we'll use this polar coordinate stuff to discuss that. And then chapter 9, just to give you a little idea about what the rest of the semester is going to be, it's going to be 8.1, 8.3, and then 2 sections from chapter 9, and those are going to be dealing with vectors. So again, using trig as our tool set to do other types of mathematics. Okay, go. Okay, so let's get into 8.1, polar coordinates. So like I said, we typically, when we want to talk about the position of a number in 2 dimensions, we use a coordinate plane with x and y, and we describe its position as some point. Oh my god, jeez, cat, are you kidding me? Okay, rude. Squeeze through a hole in the desk to get up here. Okay, so I lost my train of thought. And to what end? What end is it? Why does she want to get up on the desk anyways? All that happens is she gets yelled at. Okay, anyways. So there is some coordinate point here. I'll just call this like x prime and y prime, just some arbitrary. I could call it, 3 and 2, whatever. So this is some point, x prime, y prime. Of course, we know how to read coordinate points and how to graph points. This is so-called the rectangular coordinate. So rectangular coordinates are in xy form. In the normal, the normal form that you're used to. Are in the normal x, y form. So if you want to tell me how to get to a point, you say go this far to the right or left, and then go this far up or down, right? Horizontal and then vertical. That's why they're called rectangular coordinates, because the movement is boom, boom. Okay. There is another type of coordinate system, of course, called polar coordinates, right? You can see that coming. So that is where we have an r well, let me see, how do I want to say this? Yeah, I did not mean to say that. God. Still xy, still xy, still the same coordinate plane. That's kind of the point, is that it's on the same coordinate plane. Just two different ways of writing the same point. So say I had that same point, which was roughly there. The way to describe this point via polar coordinates is to describe its distance from 0, which we call r. So this distance here is r. It's an r. And its angle with the positive x-axis, which we'll call theta. And the coordinate point then is r comma theta. So this is a so-called polar coordinate that describes the same point, but instead of saying go left, or sorry, that's right, go right 3 and up 2, it might say go a distance of 4 at an angle of 30 degrees or something like that. Okay, so polar coordinates, it's just two different ways to get around the xy plane, that's all it is, are in the form, or in the, let's say, r theta form. Okay, that's the setup. Let me be explicit about this r and theta, though. R is the distance from the origin to the point, the straight line distance from origin to the point. Theta is the angle is the angle between the positive x-axis, well, should we say, the book says polar axis, between the polar axis, which would be the axis down here. I don't, anytime I don't need to introduce any new vocabulary terms, I don't like to. Trying to think if we need that specific vocabulary term. Is it different than the positive x-axis? I don't think so. So I'm going to say the angle between the positive x-axis and what? And the ray, well, how do I say, how do I describe this thing particularly? It's from the positive x-axis to the ray, this, as I've drawn it as a dashed line, which it is a ray technically, right? Or I guess I could call it a line segment. Yeah, it's more technically a line segment. Let's do that. Line segment, sorry. I'm thinking angle, that's why I said ray, but it's not infinite, it's finite. It ends at a point, so it is a line segment. The line segment that connects the origin to what? To the point. What point? Well, the point in question, right? So, r and theta are just what they are in this picture, right? If you can draw this picture and describe where r and theta are, then it's fine. Anytime you're trying to go from analyzing a picture into words, it gets a little bit more complicated, right? So just know that if you understand this picture, like the distance here should be r, and the angle is theta, coming from, just like we've measured all other angles, right? Coming from the positive x-axis and ending at that ray, then that's fine. Or he called it a ray again, sorry, the line segment. All right, so details now coming about the signs of these things. Details about signs. Signs is in plus or minus of r and theta. Well, it's not too weird. Theta, a positive theta, which direction does it go? Clockwise or counterclockwise? Counterclockwise. Just like we've done everything else, right? Going this way, counterclockwise. That's a positive, positive direction. And similarly, or in contrast, an angle going in the clockwise direction, so this way, is measured as negative. Okay, good. That's normal. What about R? Okay, R is a little weird. If R is positive, well, I'll just say it, a positive R, I'll describe it the same way that I've described theta. Is measured, just say normally, like some radial distance away from the origin, right? Just as I drew that picture up there. Now, this is where things get a little bit weirder. A negative R, but not too weird, is measured, how do we say, in the opposite direction. Let's see, in the opposite direction given by theta. I'll give an example. Opposite. Because theta is defining the direction here. So a negative r is measured in the direction opposite to the direction given by theta. So understand that what's happening here is theta controls direction and r controls like length of the distance from the origin to the point, right? But if r is negative, then r does command a little bit of the direction information in that it tells you to go opposite to the direction that theta wants you to go. I think that warrants some examples, so let's look at some examples. Sorry, I got all my dice and quarters and cards here for my discrete math course probability stuff. Example 1, so just following the text here, example 1, just going to plot some, we're going to plot some points. Okay. Let's plot these points. So you see we've got a sort of a nice normal example to look at. That's a 3 pi on 4 there for the angle. We've got a negative angle. We've got an angle greater than 2 pi. And then we've got a negative r. So we're getting lots of good examples here. Okay, so we want to graph the point 1 comma, so that's r comma theta, where r is 1 and theta is 3 pi on 4. Okay. Okay, so the way I do this is I have to draw a coordinate plane. Here it is. And I want an angle of 3 pi on 4, so I will think of where that is. In fact, I might even want to convert it to degrees if that makes you more comfortable. But maybe you know that this is pi on 4, right? Well, let me get my hand out of the way. This would be pi on 4. Straight up would be 2 pi on 4, aka pi on 2. 3 pi on 4 is going to land you over here. And we want to be a distance of 1 away from the origin, so, you know, somewhere, I don't know, maybe like here. So the whole distance from the origin thing, it's if you don't have circles drawn on here, like grid lines, then you just kind of have to estimate. All right, so this is the coordinate point 1, 3 pi on 4. And just to give you some more details here about how I found that, so the angle is coming from right here. That's the 3 pi on 4. So that's 3 pi on 4. 3 pi on 4. And then the distance, which I'll do in purple here, or what, blue, the distance from the origin to the point is 1. Now you may say, well, how do I know exactly where the point should go, like radially, like the distance? If you are given a picture or a graph that has grid lines on it, now when you think of grid lines, when I'm saying grid lines in an XY rectangular coordinate kind of plane, then you're thinking of like grid lines that are like vertical and horizontal, right? So if I said graph the point 2, 2, you can quickly be like, oh, it's right there. If I understand that this is 0, 1, 2, and this is 1, 2 there, then that point, you can just graph it on a grid line, right? So what do the grid lines look like in polar coordinates then? Well, that's a good question. You might have concentric circles, right, for different radial distances. So there might be like a circle. Okay. Oh, this is going to look bad. So this might be a distance, I guess I'll put it over here, a distance of 1. That's like the radial circle at a distance of 1. And then maybe another circle out here, and that's the distance of 2. That's an R value of 2. And then maybe another, oh gosh, that's a distance of 3 right there. So these are like radial distances, and then there might even be like some nice angle marks, like the classic angles, like your pi on 6, pi on 4. So if I had like my pi on 6 marked, pi on 4, pi on 3, of course pi on 2 is straight up and down, and then maybe my 2 pi on 3. It's looking like a unit circle really if you graph all these nice angles. Here's the 3 pi on 4, here's 5 pi on 6, this would be pi, right? So this is an angle measures out here, 0, pi on 6, pi on 4, pi on 3, pi on 2. So it basically looks like this is the unit circle down here at a distance of 1, and then I'm just like stacking bigger circles, right? With the unit circle is the special one with a radius of 1, and then I'm expanding to different whole number radiuses just for the purpose of having like grid lines. This is 2 pi on 3 here, this is 3 pi on 4. So if you have, sorry, let me finish this. Okay, and I'm not going to draw all of them. If you have this, then there is an exact right position to put your coordinate point as it's given here, right? If you don't have these grid lines and you're just kind of drawing a sketch, then there's nothing much better you can do than just plopping the point down and making sure you label it, right? Doing what I did here is even going a little bit further to like really make sure, you understand that this is the angle and that's the radius, the radial distance there. But if you have grid lines, then there is one correct place to put this, and for the one we just did, it's a radius of 1, so we're looking on this innermost unit circle, innermost circle here, and at an angle of 3 pi on 4 right there. Okay. All right, let's do these other ones. Part B is 3, negative pi on 6. Radial distance of 3 this time. The angle is negative pi on 6, so I know that's going clockwise, but not by much, right? It's like somewhere down here. Negative pi on 6 is like negative 30 degrees, so somewhere down here, and it's a distance of 3 away, which is further than this, but I'm not going to try and draw everything to scale. So I'm just going to put it out here and say, yep, that looks about right, 3 comma negative pi on 6. Okay. So I want to point out in the textbook, when they write the solutions, oh, is this recording? Yes. When they write the solutions to these things, all of their solutions have solid lines attaching the origin to the point. That's fine. But understand that all the problem is asking for is for us to plot the points, literally the coordinate point, right? If it makes you feel better to stick a line segment there, to literally draw the line segment there, that's fine. It's not like incorrect, but really what we're asked for is just to plot coordinate points, not line segments attached to coordinate points, right? So I just wanted to point that out if you go look at the text. Yeah, get out of here, kitty. Oh, now she's throwing stuff. Okay. Okay, I'm gonna have to pause every once in a while to play fetch with the kitty. Let's graph this point, 3 comma 3 pi. All right, let's first find out where the point should be via the angle. You have to think about where it's going to land. Do you have to look at r or theta first? I think it's easier to look at theta first and then decide the distance. Now, 3 pi is going to be all the way around, and then another pi, so that lands me on the negative x-axis. And it would specifically be at the value of 3. So 3 comma 3 pi. So you may say, wait a second, that's negative x, right? But remember, this 3 is not an x value. It's an r value. It describes the distance from 0, from the origin to this point. It's a distance of 3. Yes, if I were to mark these as like xy, if this was an xy plane, which they all are, and then I said like -1, -2, -3, you know, that's fine. I can put xy tick marks on here. I can do that. But that still doesn't change where this polar point ends up. It's at an r value of 3 and a theta value of pi. It goes all the way from here all the way around. So by the way, what is that point in rectangular coordinates? That same point is at x value of -3 and a y value of 0. How do I get, without drawing a picture, and for any of these points, how do I get from polar to rectangular? If it lands on an axis, it's pretty easy, right? Pretty easy. But what if it's out here? What if it's over here? Or what if it, part D? How would we do that? Well, that'll be the next thing that we look at. Let's do D now. D says -4 comma pi on 4. R value of negative. Okay, so finally we're getting that weird case where R is negative, so we can see what we should do here. All right, pi on 4, that's easy to find. That's right down the middle right here in quadrant 1. But my R value is 4. So theta tells me to go in this direction, right? So like for instance, the point out here I could say is 4 comma pi on 4, right? If this distance is 4 and this angle is pi on 4. But the negative value of 4 or for r, the negative value on the r value, tells me to go opposite to where theta wants me to go. So instead of landing up here, when I say opposite, I mean like pi revolutions away from that point. So like directly opposite to it all the way down here at -4 comma pi on 4. So the way I've done this problem, by graphing the point without the negative value on there and then just like reflecting it over this origin, that's probably a good technique that you should take note of. If you've got to graph one of these values that has a negative r value, or graph one of these points that has a negative r value, graph it without the negative first, and then throw the negative on there and rotate it pi radians away. Here. Okay, so just to make it clear, this is the answer, right down here at the pi on 4 angle, or opposite to the pi on 4 angle, a distance of 4 away from the origin. Okay, so another way to say this thing with the, another way to deal with this negative issue on r, well, actually, what I just did, except in words, would be to say this. R comma theta and negative r comma theta plus pi represent the same points. Do you see what I mean there? If you want to graph this, then take note of this fact, that you can drop the minus sign and graph the point where it normally would be, and then when it says theta plus pi, that means like add a pi to the angle. In other words, what does it do when you add pi to an angle? Well, it rotates it through half a whole revolution. It like flips it over to the opposite side, to the opposite, over the origin is the technical way to say that, but it flips it over the origin point. So this is like the way to write that down analytically, but I think the picture says it more clearly. Now this gets into another issue, which is that points in the polar coordinate, well, how do I say? Points in polar coordinate form are not unique. They're not uniquely defined. And that means that you can find multiple ways to define the same point. So just to take an easy example, for instance, let's just take like a pi on 4. Let's just do 1 comma pi on 4, because that's like pretty easy to deal with. This point is the same as the point, well, how can I get there two different ways? I could say 1 comma 2 pi, like a full revolution, plus pi on 4, right? The pi on 4 and then a whole revolution. So what would that be? 2 pi on 4 plus pi on 4 would be 9 pi on 4. That's like a whole extra 2 pi revolution, right? So that came from pi on 4 plus an entire revolution, right? So fraction arithmetic, I'll let you deal with that. It's just 8 pi on 4, right? Okay. And so this proves it, that the polar coordinate form of these points are not uniquely defined, because there's two different definitions for the same point. But just to give you another example, I could go the opposite direction and say 1 comma, I'll subtract a whole 2 pi revolution, subtract a whole 2 pi revolution, to get negative 7 pi on 4. I could do that, right? Just keeping in mind that pi on 4 minus 2 pi, right, is going to be negative 7 pi over 4. So that's like going from this point in a full revolution clockwise lands me at the same point. And then I could even do the thing where I say make r negative. So how would I manage to do that and make it land at the same value? Well, I would want the angle to be down here so that the negative r value would flip it back here. And what pi on 4 values down here that's like symmetric over the origin to the pi on 4 angle? Well, it would be 5 pi on 4. So that's just a direct use of this rule here, r comma theta. So in particular, well, 1 comma pi on 4 is the same as, or represent the same points as negative 1 comma pi on 4 plus pi, which of course is 5 pi on 4. Just using this rule up here. So the first two different representations of the point I got just from going full revolution, well, from here, full revolution this way or full revolution this way, and then this last one I got from that sneaky business about making r negative, right? But still, the point is the same for all of them, that the points in polar coordinate form are not uniquely defined. It's different from rectangular coordinates, right? You can't, how do you describe multiple ways to get, you know, in rectangular coordinates, if I give you the point 2 comma 3, there's only one way to say that, right? Okay, so now I want to get into the relationship between polar coordinates and rectangular coordinates. So, and this issue of non-uniqueness is going to come up. Okay, just using this symbol to say going back and forth between polar and rectangular coordinate. It's not like a double implication, like an if and only if. It's not that. It's just saying here are the notes for getting from here to here and vice versa. And the equations are, well, we already know them. Whether you remember them or not, we've talked about them, that x is equal to r cosine theta, and y is equal to r sine theta, and maybe a picture will help. Hang on, before I write down the other relationships. So the point out here is an xy point, so we've got some x value down here, right, from here, that's some x value, and then out here is some y value, so of course I can describe this height as a y value and this distance here as an x value, and then that distance there is r, and then this angle here is theta. So okay, let's pull this picture out. We have r as the hypotenuse, theta as this interior angle down here, this is x and this is y, and understanding that cosine is equal to adjacent over hypotenuse can get you to this relationship with a little bit of algebra, and understanding that sine of theta should be equal to opposite over hypotenuse, scoot it around, a little bit of algebra will get you there. And then what is the relationship between, or rather, this is for if you have r and theta and you want x and y, right? So this is getting from polar to rectangular. What about the other way? Well, what is r equal to in terms of x and y? Of course, Pythagorean theorem. Whoops. Square root, right? Because r squared is equal to x squared plus y squared, so I'll just go ahead and fully solve for r by throwing a square root over there. All right, and then theta is equal to tangent inverse of y over x. Why are we using tangent inverse instead of sine or cosine? Well, because sine and cosine would both involve the hypotenuse of r, right? But we're assuming we only know x and y, because these, finding r and theta, you're given x and y, and you want to find r and theta. So over here, we better use some trig function that only involves x and y, and tangent is the one that does that. That's why we're using tangent inverse of y over x. I should say this only works, right, if x is not 0. So it won't work for any angle on the y-axis. But if the angle is on the y-axis, then it's either pi on 2 or 3 pi on 2, right? So that's an easy case. Same thing if the angle's on the x-axis and the y value is 0, then it could either be an angle of 0 degrees or pi degrees. Or 2 pi. Well, 0 or pi, right? 0 or pi. 2 pi is the same as a full revolution, so you could just say 0. Okay, so these are the relationships that we want. Let's see, I could technically put a plus or minus, I suppose, on the square root, which would be typical for how you would solve an equation. You would put a plus or minus on the square root, but do we need to worry about that? Because we can always make r positive just by scooting the angle, right? So maybe we won't worry about that unless it unless we really have to deal with that. So we'll deal with that if it comes up. Now about that issue where points in polar coordinate form are not uniquely defined, that means that when we're going from rectangular to polar, we're going to have to be careful to make sure we're getting the right point and everything, and that'll come from what quadrant the XY point was in. So we'll do some examples to show you that. So first of all, though, let me just make this clear. This is going from polar to rectangular, so I'll say P to R and use these, and then from rectangular to polar. All right. Let's do some examples. So I skipped example 2 because I basically did example 2. Example 2 in the text was about this issue of being able to define points multiple ways. So I went ahead and skipped explicitly writing down example 2. So this is example 3 from the text, which says find rectangular oh my goodness, can't read. Find rectangular coordinates for the point that has polar coordinates 4, 2 pi on 3. Okay. Yeah, I'm gonna just say it's pretty obvious that the point is in polar coordinates if it's got a 2 pi on 3 in the second position. Pretty obvious that it's in r theta form. Okay. Alright, so we've got r and theta. Let's find x and y. X is going to be equal to 4 times cosine of 2 pi on 3, so we're going to have to recall what 2 pi on 3 inputted into a cosine function is. In fact, just for fun, I'll do that from scratch. So 2 pi on 3 is in the second quadrant, right? So maybe I'll orient it like this, just to remind myself that this should end up giving me a negative x value, because cosine is negative in the second quadrant. Okay. Draw my reference triangle here. This is a reference angle of pi on 3. That's a 3, too tiny, can't see it, but that's pi on 3 in there. And the reference triangle looking like this should have side lengths 1 and square root of 3 and 2, where in particular the x value is negative. Maybe it looks like bad to have a negative value on the length of a triangle, but remember that I'm thinking of this as being just a triangle that I'm drawing on the coordinate plane. So this is representing literally like -1 out here, -1. And the height up here is at 2. Okay. And then of course the angle of 2 pi on 3 is right here. That's the 2 pi on 3. Okay, so long story short, cosine of 2 pi on 3 is 2 pi on 3 is -1 over 2. So we're getting 4 times -1 over 2, which of course is -2. Nice. Now y is equal to 4 sine of 2 pi on 3. Well, we've already got the triangle drawn, so I can just do opposite, which is positive, right? In the second quadrant, the y value is positive. Square root of 3 over hypotenuse 2. And that's giving me 2 square roots of 3. So the coordinate point in xy form is -2, comma, 2 square root of 3. Good. All right, let's go the opposite direction for finding polar coordinates from rectangular coordinates. Xy is 2, -2. Okay, so our equations for this are, maybe I'll leave it in this format this time. R squared is equal to x squared plus y squared. And theta is equal to tangent inverse of y. Oh, hang on. Did I write that other one? Okay, y over x. Had a moment of panic, thought I wrote it as x over y for some reason. This is right. Alright, so I should note again that since we're finding polar coordinates, that I need to be wary of these points, making sure my point's at the right spot, right? So what quadrant am I in? I should note that. Note 2, -2. Let's see, x is positive, y is negative, so is in quadrant 4. So I should note that. That'll be helpful in finding the angle. Let's go ahead and find r, which has nothing to do with the angle, but so this note is going to be more useful when we find the angle, but anyways, let's find r. Okay, I'm going to work horizontally this time, so r squared is equal to 4 plus 4. R is equal to square root of 8. We'll leave it positive. Because again, you have a choice, but why complicate it, right? You could make R negative and then adjust your angle, but why, right? Why would you do that? Just to make things, I mean, maybe there's some situation where you need to do that, but I can't think of one. Okay, so square root of 8, right, is 2 square root of 2. All right. Okay. Now for the angle, theta is tangent inverse of -2 over 2. Simplify inside that fraction, tangent inverse, or arctangent if you like, tangent inverse of -1. Now, what kind of angle? So when you get to this point, you still have to answer the question, like, what kind of angle gives me this tangent inverse of -1? Well, I know that tangent represents like the y over x values, right? So if I'm looking at that unit circle, I'm looking for coordinate points that are the same, except one of them is negative. Why do I say that? Well, because when you stack them on each other, you get a 1, so they must be the same. So in other words, I'm looking for those coordinate points that where the x and y value look exactly the same, in other words, pi on 4 angles, right? But one of them is negative. One of them is negative. So that's telling me that theta is either, where is only one thing negative? In quadrant 2, which is the 3 pi on 4, or theta is the one in quadrant 4, which is 7 pi over 4. But of course, I've already noted we're in quadrant 4, so this is the angle that we want. So the coordinate point in polar form is that. 2 square root of 2 for r, 7 pi over 4 for theta. That's a good point. I neglected the whole range of the tangent inverse function. What? Tangent inverse, its range is only supposed to be on over here from negative pi to pi, right? So really we should describe, I mean, this isn't incorrect though. So the book says the answer is, what's the difference here? The book says the answer is this. Because they're putting their angle, they're making sure that their angle agrees with the range of the tangent inverse function. Whereas I just pretty much like brushed it to the side and said I don't really care to think of tangent inverse as a function, because when you're thinking about the geometry, which is what we're doing here, right? We're thinking about a picture. I don't really care how I describe my angle as long as it lands me at the point that I want. In fact, I would prefer to think of it not as a negative angle. By the way, these are the same angles, right? These describe the same angles. It's just that this one is described in this range. This 7 pi over 4 one, it goes all the way around outside of the range of the tangent inverse function, and it lands in the same spot, of course, down here, which is where we know it is, but it goes outside of technically of the range of the inverse tangent function. So they describe it so that it just goes right down here as a negative pi on 4 angle, the whole thing staying in this range. But when you're talking about converting polar coordinates, or converting coordinate forms, right, rectangular to polar in this case, I just don't think you need to worry about these domain and range, well, specifically range issues for like the inverse tangent, because when you really get down to it, we're talking about pictures here, right? Coordinate points on coordinate planes, and the geometry does not care what the range of the tangent inverse function is, right? Remember that was a big deal when we were specifically talking about the function nature of this thing, right? It very much it was a big deal back then. But here, when you're just using it, I think we can be a little bit more loose, and I would say that either of these is acceptable. Either of these is acceptable. Oh, and in fact, they list another solution, like if you decide to really like punish yourself and think of one where you could make the r value negative. What would you do then? Well, you could go a whole pi rotation away from these angles, and what would it be? Well, a whole pi rotation away from 7 pi on 4, like if you went backwards to land up here in the second quadrant, then that would be 3 pi on 4. So you might say, well, wait, I thought we were in quadrant 4. Well, we are, but remember when you stick a negative on the r value, it flips you opposite to where the angle tells you to be. So this is just another way to write this answer. So all three of these are describing the same point. They're all describing the same point. I like this one the best. No negatives. I can see why this one is technically the best because of that range issue, and I just don't think anyone would want this one. Now for the last bit of this video, I want to talk about some things that I'm not going to hold you accountable for knowing on exam or homework, but you will need to know for if you're going into the calculus sequence. So I'm just going to do a quick and informal example here. So consider if we have if we're asked to graph r equals secant of r equals 5 secant theta. If we're asked to graph this equation, it's an equation. It's an equation in polar form. That's how I would describe this. Whoops, that's a Q, not a G. Equation in polar form. And we're asked to graph it. Well, how the heck do you graph this, right? Other than just asking Desmos to do it for you. Well, there's a trick to this, which is to say, put it in rectangular form and see if it looks easier. So try putting it, and this is a theme that you do in like Cal 3 or Cal 2, I can't remember. Try putting it in rectangular form. And sometimes you'll put rectangular form equations in polar form because they're easier to deal with in polar form. So how could I do that? Well, I know that, what do I know? X is equal to r cosine theta, and y is equal to r sine theta. Why is that helpful here? Well, look at this. R then is equal to x over cosine theta. So what if I just shove that in for r? What happens then? And then I'm going to try to get rid of all the trig functions. Let's just see what happens. X over cosine theta is equal to 5 secant theta. But what is secant theta? It's 1 over sine. Nope, sorry, it's 1 over cosine theta. Right? Look at that. Multiply by cosine theta on both sides, these things go away, and we just end up with x equals 5. I mean, how nice is that? You can graph that, right? Can you graph this? Well, if I didn't tell you all this stuff, you might go, no, I can't. I don't know how to graph that. But if I tell you that you can convert it to this form, you can surely graph that. That's just a vertical line at x equals 5 right here. I'll do it in red. That's just a vertical line at x equals 5. But it's also r equals 5 secant theta. Though that is much harder to think about than the equation in rectangular form. So this is a technique that you'll find useful in calculus. Either taking something that looks awful in polar, well, at least not recognizable in polar form, converting it to rectangular form for the purpose of graphing, or maybe integrating it or something like that, or vice versa, taking something that looks really weird in rectangular form and graphing it in polar form, again for the purpose of integrating it. In fact, or graphing it. There's a pretty popular integral that is so-called it's not integrable, at least in, I don't even want to get into it. Never mind. Okay, so not holding you responsible for knowing these. This is example 5 and 6. This kind of describes the techniques used in examples 5 and 6. You can look at them if you'd like, but not responsible for it in the homework or the exam, just a little extra thing. All right, that concludes section 8.1. All right, Katie, I'm done.